So last day we were looking at unit conversion, and we finished off, so my argument was I hate memorizing stuff. I think my first lines, the first thing I said was I don't like to memorize things. So I tend to build these fractional chains, and I figure out whether I need to multiply or divide based on whether the number is on the top of the fraction, multiply, or on the bottom of the fraction, divide. And I figure out where the number goes by looking at what units need to cancel. Oh, I got a latecomer here. Excellent. So I build fractional chains. Are there shorter ways to do this page? Yeah. And I know some kids memorize shortcuts, especially for metric conversions. There's ways that you can get there kind of by counting and figure out what the power of 10 is. I've never bothered learning the shortcuts because I got a 2-second method, one size fits all that works, and so I'm good with it. And I think it's a very similar method to those of you that are in chemistry. Mr. Perugia was showing you something very, very similar. I showed you a little video, well, a phone call. I tried to convince you that units do matter, and so I will be fussy on units. And then we said we can build chains to convert things, Krisha, using knowledge we already have. That's kind of a handy skill as well. Then we started dreaming about lottery wins. So we looked at Gloria McKenzie, who has the grand prize lotto, and we found that $1,000 per day, it would take her 1,618 years to spend that much money. We found that if she spent $500 per hour, it would take her 134 years, 135 if I round off. So then we asked, okay, she only took 371 million. She took the front end payment instead of having it paid out over time. What if she spends 10 bucks a minute? And this is where we pause. Yes? Okay. So my strategy was I always write down what they give me. I wanted a strategy that was kind of a no-brainer strategy. So whenever I'm doing a unit conversion, I write down what they gave me. And then I start to build a fractional chain. Here they gave me $371 million right there. I divided it by $10 per minute. I divided it by 10 to figure out how many minutes. So it's going to take her this many minutes, and we want to convert that to years. Where am I going to want minutes in the next fraction? Top or bottom? Bottom, so it cancels. Do I know how many minutes are in a year? No. What can I convert minutes to? That would go away from, I want to get bigger time frames though to get to a year. So yes, I can convert it to seconds, but I think I want to go in the other direction. So, hours. 1 hour, 60 minutes. I want hours to cancel. Do I know how many hours are in a year? Conveniently in this lesson, we did actually calculate that. Now, if we didn't know that, we would go from hours to days, and then from days to years. But I think we do have the conversion factor. Wasn't it 8,000 something? 8,760? So, whoops. 1 year is 8,760 hours. And again, I don't have that memorized. I can always rederive it in 1 second. And this would give us an answer in years. I think we're going to go 371 with 5 zeros, divided by 60, divided by 8,760. And I get 70.6 years. Can she do that in her lifetime? If she won this prize while she was young, like if she won this prize in her 20s and she lives into her 90s, she can pull this off. But even that, I mean, if she won it while she's middle-aged, nuh-uh. It's staggering how big a number a million is, or a billion is, or a trillion is. In fact, most of us don't have a very good understanding of that number. Put your pencils down. This is a website, it's called the Mega Penny Project. And what it does is it looks at numbers in terms of pennies. Now I realize in Canada, this is a US website. In Canada we phased out the penny, but you all remember what they look like and how big they are still. Yeah? So let's take a walk through some numbers, and we're going to start to try and imagine what these numbers would look like in terms of stacks of pennies. So we start out 1 penny. 16 pennies would look like that. No big deal. Well, 16 pennies in the US is 1 inch high, and in the US they still use inches. So there is 1 that high worth of pennies. What would 1,000 pennies look like? $10. Okay? It would be 5 pennies wide, 5 pennies deep, 40 pennies tall. 5 times 5 times 40 is 1,000. It would weigh 6.25 pounds. You could carry it. Now let's build a 12-inch cube, a 1 foot by 1 foot by 1 foot cube of pennies. How many pennies would that be? That's just shy of 50,000 pennies, just shy of $500 worth of pennies. $491.52. So that would be a stack of pennies like this. Its mass would be 300 pounds. You could not carry it. If you stacked it, it would be 256 feet high, about 25 stories high. So there's 50,000, almost, not quite 50,000 pennies. What would 100,000 pennies look like? 2 of those. 2 of those. 100,000 pennies. 2 of those. And now, Kennedy, we're going to get bigger. What comes after 100,000? What would 1 million pennies look like? Try and imagine what that would look like. 1 million pennies. Well, kind of like this. Okay? When someone says to me 1 million, this is one of the images that flashes into my brain. If we have an adult male standing, it would be stacked up high like that and a little bit left over. It's a wall 5 feet by 4 feet by 1 foot thick and a little 9-inch cube step stool. If you stacked 1 million pennies, it's almost but not quite 1 mile high, so about 1.6 kilometers high. So there's 1 million. What would 10 million look like? Well, 10 of those, I guess. What would that look like? Okay. So there's 10 million pennies. This is a cube. It's a little bit more than 10 million pennies. It's 10,017,000. But you know what? Close enough. If you laid them flat as a carpet, it would pretty much cover a whole acre. If you stacked them, it's almost 10 miles high. So that's getting pretty high. So there's 10 million. What comes next? 100 million. What would 100 million look like? And now, 100 million, we're getting into the same numbers as Gloria won in her lottery. She won 590 million. Took 371 million or whatever it was. So 100 million pennies look like that. If you stacked this, it would be 99 miles high. That's approaching, not quite, but that's already getting into what we would call outer space. It would be in the very thin or non-existent atmosphere. I think the ISS orbits at around 140, 150 miles high, although its height varies because they can raise it or lower it. What comes after 100 million? 1 billion. Okay? 1 billion. What would 1 billion pennies look like? Try and imagine it. About like that. If you took a school bus full of pennies, 5 school buses made out of pennies. 1 billion. If you stacked this, it's almost 1,000 miles high. This is well into outer space, into low Earth orbit. By the way, little note, 1 billion is only 1 billion in North America. In Europe, this is not 1 billion. In Europe, this is 1 million million. In Europe, when they talk about a billion, they actually mean a million millions, which we call billion, trillion, quadrillion. And if you don't think that leads to some confusion in world money markets, it does. So a billion in North America is different from Europe. Hashtag nerd trivia, but there it is. Okay. 10 billion. So we talk about BC having a deficit or a debt in the billions of dollars. 10 billion. You can still see little person right there. That's 10 billion pennies. Canada has a deficit or a debt, I believe we're in the 10 billion range. You stack that, oh, now it's really high. It's about 10,000 miles high. What comes after 10 billion? 100 billion. 100 billion. Oh, 10 billion. So I think Bill Gates is still, projector gone. Projector comes back. Bill Gates is still, I think he's still classified as the wealthiest person on earth. He's about, I think, 25, 30 billion. Okay, so he's got 3 of those. 100 billion. See a little person there? Okay, there's 100 billion. Now we're talking about budgets of entire large countries. The US military budget probably is somewhere around this, for example. What comes after 100 billion? Well, what comes after billions? Okay, what would a trillion look like? Oh, hang on, before we get there. The total number of pennies now in circulation in the United States. So in the United States, it's estimated that there are about 200 billion pennies floating around. Most of them are out of circulation, are missing. They're in sock drawers, they're underneath car seats, they're down in drains, they're in wishing wells, they're out. A lot of them are missing. It's why Canada eliminated the penny, because it was costing more to make the penny than the penny was worth. Okay? So about 200 billion pennies in circulation. Now, trillion. What would a trillion look like? I don't know if you guys in the back can see, but Bryce in the front can see. Little guy, there's the person. Right there. There's a trillion pennies. The U.S. debt, I believe, is around $6 or $7 trillion. Okay? Countries tend to spend more than they make because nobody wants to save money and lose the election. They want to spend money to win the election. It's just the system. Let's look at this a little more closely to get a better idea of its size. So here's a trillion. Some famous buildings. Here is the Sears Tower in Chicago. Here is the Empire State Building. Here is the U.S. Washington Monument. And there is a trillion pennies. Yeah, and there's our token football field like we have in the back. And of course, now it leads to the obvious question. If we have the Sears Tower, if we have the Empire State Building, how many pennies would it take to fill the Empire State Building? It turns out, if you wanted to build the Empire State Building out of pennies, about 1.8 trillion. Almost 2. Hey, what about the Sears Tower? If you want to build the Sears Tower, about 2.6 trillion pennies. Ish. Okay. What comes after trillion? Quadrillion. What would a quadrillion pennies look like? The little man is now smaller than a pixel, so I can't show you the little man. You can see the football field here. Well, there's a quadrillion pennies. And we're going to go one more. What comes after quadrillion? Quintillion. What a quintillion pennies look like. There's the quadrillion. There's the buildings. The football field, I think, is about 1 pixel. I think there's a little dot there. There's a quintillion pennies. Mr. Derek, do your numbers get that big? Sometimes. Not financial numbers. I think it's estimated, if you add up the world economy, it's in the trillions, not in the quadrillions or quintillions. Is that okay? Just showing you big numbers and small numbers. Okay? Okay. Back to our notes, please. We're going to go off on a little tangent, and then I'm going to give you the rest of the class to work on the homework, and we're done the unit. Enrico Fermi was a physicist, very famous physicist, brilliant at being able to solve very, very complicated problems to within an order of magnitude. That's fancy speak. Say what? He was good at solving really complicated problems in his head, and if you wrote the answer in scientific notation, he'd have the 10 to the right. He might not have the front part right, the 5.6 time, but he'd always have the 10 to that. In fact, this is a true story. He was at the very, very first test of the atomic bomb, called the Trinity test, and he figured out how strong the atomic bomb was before anybody else. And the way he figured it out, he held a piece of paper flat, and when the shock wave hit him, he let the piece of paper flutter back, and by measuring the distance, he thought for a little bit. He said, you know what? The atomic bomb was about this strong, and he was pretty close. He did what's called an order of magnitude approximation. Well, I'll tell you what he did. Put your pencils down still, look up. So these are called Fermi problems. You can scribble out the practice. But for sort of fun homework, I'm not going to ask you to hand this in. I'm just going to talk about this next class. If you want to see if you can come up with an estimate, so if Pitt Meadow Secondary School, actually right now we have 900 students. Estimate the number of pieces of note paper that the entire student body would use in an average year. See if you can come up with a good guess and convince me of your reasoning. And this is purely for your own nerdiness. I'm not marking this. And then number 2, see if you can estimate how many breaths are taken each day in BC. And again, I'm not marking this right or wrong. I'm looking for, can you give me a good argument? You can work with a partner on your own. And this is not homework. I'm not going to collect this. But next class, I will start out by asking how you did, if anybody has any suggestions. What is your homework? I have a sheet here called Unit Conversion Practice. Answers, it says, will be posted online. Actually, I have 6 answer keys here if you get stuck as well.